How's it going, everyone, and welcome back to another video. Today we're going to be going through the NumPy library, which is considered to be kind of the fundamental package for all scientific computing in Python. So it's a super important library. It's kind of the base for a lot of the other major data science libraries in Python. So like Pandas that I've done a video on before, it builds pretty much entirely off of the NumPy library. So it's super important, and kind of because it's important is because it's this base. The way we're going to do this video is I'm going to start out with kind of a background information on how NumPy works, and I think really having that intuition is helpful for when you actually start writing code with it. So we'll do the background information, and then after that we'll jump into all sorts of useful methods and ways you can utilize this library as far as actual code goes. As always, make sure to smash that subscribe button, throw this video a thumbs up, follow my Twittergram, Instagram, Twitter, GitHub too, hit the bell for the notifications, throw this another thumbs up. Yeah. To begin, NumPy is a multi-dimensional array library. So what that means is that you can use NumPy to store all sorts of data in one-dimensional arrays, two-dimensional arrays, three-dimensional arrays, four-dimensional arrays, etc. And so the common question you kind of ask, or I'm commonly asked when you first bring up NumPy, is why do you use NumPy over lists? So the main difference comes from the speed. So lists, they are very slow. Meanwhile, NumPy is very fast. And so why are lists slow and NumPy fast? Well, one reason is because NumPy uses fixed types. So what that means is, imagine we have this 3x4 matrix, 3 rows, 4 columns, and it's all integer values. And we're going to kind of look at how those integer values differ between NumPy and lists. So let's just zoom in on that 5 that's there in that matrix. So our computers, they don't see 5, they see binary that represents 5. And so this is the number 5 in binary, and it's 8 bits, which makes up a byte. So our computers read information in bytes. So when we use NumPy, this 1-bit 5 is actually by default going to be casted to this int32 type, which consists of 4 bytes. And so it represents 5 in a total of 4 to be casted to this int32 type, which consists of 4 bytes. And so it represents 5 in a total memory space of 4 bytes. So int32, and you also can even specify, so by default it's int32, but you could even specify that you didn't need all 4 bytes to represent this value. So you could specify within NumPy that you wanted maybe an int16, which is 16 bits or 2 bytes, or even if you had really small values, int8, which is just a single byte. On the other hand, with lists, there's a lot more information you need to store as an integer. So in lists use a built-in int type for Python. And so that built-in int type consists of 4 different things. It consists of the object value, which has its own bits associated with it, object type, the reference count, how many times that integer has been specifically pointed at, and the size of that integer value. And so if we break this up into the actual binary that it represents, we can take the object value, and that's represented as a long, which is 8 bytes. The object type, same deal. Reference count, same deal. And then the size, I believe, is a little bit smaller. I think it's only 4 bytes. But as you can see, that's a single integer within lists using the built-in int type. It requires a lot more space than NumPy. So basically the takeaway from this is that because NumPy uses less bytes of memory, the computer can read less bytes of memory quicker, obviously, so it's faster in that regard. Another reason that I didn't specifically say is that when we're iterating through each item in a NumPy array, we don't have to do type checking each time. So in Python built-in lists, you could have a list of an integer, then a float, then a string, then a Boolean. And you'd have to check each element you're looking at, what type it is. But NumPy, we don't have to do that. So another reason it's faster is that there's no type checking when iterating through objects. Moving on, another reason that NumPy is faster than lists is because NumPy utilizes contiguous memory. So what that means is, imagine that this kind of array-like structure is our computer's memory. So we could store information in any one of these memory blocks. So if we had a list, the way that would look in a list's memory is that our list would be kind of scattered around. So maybe we have a list that takes up 8 memory blocks. The thing is that these memory blocks aren't necessarily next to each other. So you have some information here, you have some information here, you have a good amount of information in here, then you skip a block here, here, and skip 2 blocks, you have some information here. So it's all kind of scattered around. So kind of, if you have an 8-item array, what that looks like is that array is actually just, or that list is just containing pointers to the actual information that's scattered around our computer's memory. And so it's just that all the information is not right next to each other. You have to bounce around your computer's memory a bit, and it's not super fast to rapidly go through and kind of potentially perform functions on all items at a time or subsets of the items. NumPy array, however, uses contiguous memory, so all 8 blocks in this case would be right next to each other, and this has all sorts of advantages. And also, just to mention real quick, you'd also kind of have to store somehow where the start of that memory is, and then the total size and the type of memory block. But it's a lot easier than this kind of pointer structure that's up here. And so the benefits of NumPy using this contiguous memory are a couple of different things. So the first benefit is that our CPUs, our computers, have these SIMD vector processing units. And so when this memory is all right next to each other, we can utilize this unit. And basically what SIMD stands for single instruction data. So we can, like, if we have to do an addition of like a lot of values, instead of just doing one addition at a time, we can use this SIMD vector unit and basically perform computations on all of these values at one time. So it's quicker in that regard. Another reason it's quicker is that we more effectively utilize our cache, so our quicker memory in our computer. Basically, if we load in all these values, we can keep them close to where we need to access them, and like perform all sorts of operations, while as in the lists case, you'd maybe load in like half of this, but then this other half, because it's scattered around in different places, you'd have to like go back and like reload that in to your cache, like, you know, just be overall slower, because you'd have to do more like longer memory lookups within your, you know, just that it's scattered around in different places, you'd have to like go back and like reload that in to your cache, like, you know, just be overall slower, because you'd have to do more like longer memory lookups within your computer. Okay, so we kind of went over some of the performance benefits, but how are lists different from NumPy? Well, lists, we can do insertion, deletion, appending, concatenation, etc. And we can also do those same exact things in NumPy. I guess the big difference, though, is that within NumPy, we can do all of that, and we can do lots more, and we'll see the lots more throughout the video. But as a simple example, imagine we have these two arrays. One thing that we can do that's really nice in NumPy is that if we try to multiply these one item at a time, we could do that in lists. You couldn't multiply 1 and 1, 3 and 2, 5 and 3, etc. But when we do the exact same computation within NumPy, it allows us to do these, you know, single value, like item-wise computations, which is pretty neat and pretty useful. So that's one example, and you'll see a lot more throughout the video. So applications of NumPy. There's all sorts of applications. I think the first one, the first one that comes to my mind is a kind of a MATLAB replacement. You can do all sorts of mathematics with NumPy. And I think I should say that I think the SciPy library has even more mathematics, like functions and whatnot. So if NumPy isn't cutting it for you, try to look through the SciPy documentation. You might be able to find even more. But yeah, it's pretty powerful, the math that NumPy can do. It's useful in plotting. It is the back end of many different applications. So pandas, which I've done a video on before, it is just like the core component of pandas library. It really allows pandas to work. If you've seen my Connect 4 how to program that video, I use NumPy to store the board use machine learners are the NumPy. All right, to get started with the code, the first thing you're going to want to do is import the NumPy library. And just so we're on the same page, I'm using a Jupyter notebook to use to code this up, but you can use whatever editor you prefer. Also, all of this code that I'll be going through will be on my GitHub, and the link to that will be in the description. Okay, so import numpy as np. If that worked for you, great. If it didn't work, you'll have to do a pip install. So you can go ahead into your terminal and type in pip install numpy. And so it's already installed for me. So, and if pip doesn't work for you, try pip3 install numpy. That should work. So the first thing, np.array, and then within this we just basically pass in a list. So 1, 2, 3. This would be a one-dimensional array containing the values 1, 2, 3, as you see. And you can go ahead, if you're not using Jupyter Notebooks, and print A. Okay, cool. So we could also initialize a little bit more complex arrays. So we could do like a 2D array of floats, and I could do that the following way. We're going to have a list within a list. So here's some float values, and then we're going to make this two-dimensional. So here's some more float values. And let's go ahead and print B. Cool. So now that we know how to initialize arrays, and you can keep doing this, like I can nest list within a list within a list to create a three-dimensional array, etc. Some other useful things to know about this is how do you get the dimension of your NumPy arrays. So if I did a dot number dimensions, so this tells me that it's one dimensional for A, and if I did b dot n m, it would be 2. Shape is another important function, so get shape. If we do the first one, a.shape, this is all we have to do. It's a vector, so it's only going to tell me the one dimension because it only has one dimension, so it's size 3. If I do b.shape, it's going to tell me the rows and the columns, so this is 2 rows and 3 columns, so this should print out 2 by 3, as it does. Okay, other things, we want to know how much memory our NumPy arrays take up, so we can get the type and also get the size. So if we want to get the type, we do just a.type, a.data type, int32 by default. So even though these are small values, by default, it specifies that it should take up 4 bytes or be an int32. If we wanted to specify what type we wanted to store as, so maybe we knew that we didn't have many like big values, so we could do like an int16, and so that would take up less size, and you can see we could do like an int16, and so that would take up less size, and you can see the difference in size in a sec. So right now it's int16. If I want to see the size, there's a couple different, I guess. So right now size, so we could do like an int16, and so that would take up less size, and you can see the difference in size in a sec. So right now it's int16, and we could do like an int16. And so that would take up less size, and you can see the difference in size in a sec. So right now it's int 16, and if I want to see the size, there's a couple different, I guess, important functions with this. We could do a.item size. So this should tell me 2 bytes, as it does. If we left this as an int 32, it will tell me 4 bytes down here, as it does. You can also do, I think, the total size. I guess a.size is the total number of elements. So the total size would be a.size times a.item size. Another way to do that is, I think, just number of bytes. As you see, that's the same thing. And you can also do this with b. So like b.item size. B's are floats, and I believe that this is an 8-byte type. So if I do b.item size, as you see, yeah, it's 8. So floats are going to be bigger than integers usually, unless you define this as like an int 64. And so, yeah, I usually don't even worry about the data type too much. I don't specify it, but if you really want to be efficient, try to specify this so that it fits all your data, but I guess it fits all your data as tightly as possible. All right, so now that we've gone through some of the basics, let's actually show how we access / change specific elements, rows, columns, etc. So imagine we have the array. There's going to be a 2-dimensional array, so I'm going to make this kind of long, and you'll see why in a second. Okay, so this is a 2 by 7 array. If I print that out, okay, and I could prove that it's a 2 by 7 by doing 8. Shape, that's just a reminder. So what if we wanted to get a specific element? Well, to do that, we can use this notation of row, comma, column. So this is the row row index, this is the column index. So I could do something just like a, let's say I wanted to get this 13 right here. Well, that would be in the second row, but because we start Python indexing at 0, be the first row, and then the 0, 1, 2, 3, 4, 5, fifth column. So yeah, that gives us the 13 as you see down here. And one thing that's kind of cool is you can also use the negative notation similar to lists. So I could also say the negative second element would be 13 as well, because this would be -1 and then -2. So there's a couple different ways to do this, but we'll stick with the first one. Okay, let's say we wanted to get a specific, I can't spell, row. That's pretty straightforward as well. So in this case, if we wanted the first row, we would do 0, and then because we want all columns, we use the basic slice. syntax similar to lists. And I can just do a single column, and that will get me everything in the row. Lists. And I can just, because we want all columns, we use the basic slice syntax similar to lists. And I can just do a single column, and that will get me everything in the row. That's nice. What if we want a specific column? Well, if you know how to do rows, you probably know how to do columns. Let's say we wanted this row or this column right here, 3 and 10. That would be all the rows and then the 0, 1, 2 column. That gives me the 3, 10. And from here we can do even some more like tricky stuff. So I'm going to just say getting a little more fancy. And we have the start index. This is just a reminder, start index, end index, and then finally the step size. So if I wanted to, let's say, get between the numbers 2 and 6, every other element, so 2, 4, and 6, well, to specify that, I would do, well, I want the first row, and then I want to start at the first element, the 2, and I actually screwed that up, it should be 1. So I start at the 2, then I want to end here at the 6, which is the, it's exclusive, so that would be, I want to actually go to the 6th element, and then I want to step by 2 because I wanted 2, 4, 6, so I do 1, 6, 2, and that gives me 2, 4, 6. And I can also use the negative here and do like -2. What happened there? Oh shoot, that was going backwards. I didn't want to change it there. I wanted to change the 6 to be -2. Okay, it's exclusive, so I wanted this to actually be -1. A little bit more of a fancy way to do that. Okay, so that's how you access elements. And then if we wanted to change something, it's pretty straightforward too. Let's say I wanted to change that 13 that I originally accessed. Well, I can just do like 20. If I print out A now, that original element that was 13 is now 20. And you can do the same thing for series of numbers. So like for an entire column, let's say we wanted to replace this 310 column, I would do something like series of numbers. So like for an entire column, let's say we wanted to replace this 310 column, I would do something like a colon 2 equals, let's say I wanted it to be all fives. I could start like this, and as you see, it's all fives, 5, 5. And then if I wanted it to be two different numbers, you just kind of specify all fives, 5, 5. And then if I wanted it to be two different numbers, you just kind of specify the same shape as what you've subsequenced. So it'd be like 1, 2. So now you see that we have a 1, 2 in that position. Really quickly, let's just show a 3D example. So it'd be like 1, 2. So now you see that we have a 1, 2 in that position. Really quickly, let's just show a 3D example. If I had a 3D, so we'll say B equals numpy array of all of this, and if I print B, so if we want to get a specific element here, The recommendation I have is work outside in. So work outside in. So let's say I wanted this 4 right here. Well, the farthest outside would be which one of these do I want? And I want the first set, so I want this area right here. So if I wanted that, I would do B, 0, and then now that I'm in here, I want the second row. So I want the 3, 4, so that would be 1, and now that I'm within this, I want the first, or the second, the second element, but the first index, like that. So that gives me the 4. And you can do similar type stuff with like the colons in here. So each one of these dimensions that you're indexing, you can be all fancy with how you access elements. So I can do something like this and, get 3, 4, 7, 8. And you can kind of play around with this and see how changing different things changes what you get. And if you wanted to replace in this case, basically you just have to create a subsequence that's the same dimension. So if I did B1, that gives me 3, 4, 7, 8. Let's say I wanted to change that to 9, 9, 8, 8. As long as it's the same dimension, it's going to work. So 9, 9, 8, 8. If I try to do something like 9, 9, 9, 8, 8, it's going to have an error. All right, so that's the basics of indexing. I think at the end of the video, I'll do a little challenge problem on some advanced indexing. So look at the end of the video for that. All right, next let's go through how to initialize all sorts of different types of arrays. So to start off, let's initialize an all zeros matrix. And to do that, there's a nice built-in function called np.zeros. And we can first, I guess actually all we really need to do is specify a shape. So I did np0 is 5. It's going to just give me a vector of 5, length 5. But I also can pass in a more complex shape. So if I wanted it to be like a 2 by 2 or 2 by 3, let's say, as you see there, I could do 3-dimensional, 2 by 3 by 3. Could even do 4-dimensional if I wanted to. 2 by 3 by 3 by 2. It gets pretty crazy, but yeah, you can do all sorts of zeros with that. Next, let's do an all ones matrix, pretty similar to the last one, and p.ones of, let's say, 4 by 2 by 2. And there you go. And you can also specify the data type here. So if you wanted like all ones but in 32, you can go ahead and do that. So all ones, all zeros. However, you might want to initialize a matrix that's not ones or zeros, any other number. So for that, you can do np.full. And this one takes in two parameters. So it's not all zeros. However, you might want to initialize a matrix that's not ones or zeros, any other number. So for that, you can do np.full. And this one takes in two parameters. So the first is the shape, so 2 by 2, and then the next is the value. So if I wanted all 99s, then it's a 2 by 2 with 99. Another useful, and you can, that has a data type too. So if I wanted that to be float 32, there you go. And I'll put a link in the description to a list full of these like array creation routines. Useful to know is there's also this full like. There's this full like method, and basically that just allows us to take a shape that's already built. So let's imagine we wanted to reuse that this array that we had in the last section, A. Well, I think it's still loaded in. Let me just make sure. Well, I can pass in and make a array that's the same size of 4s, let's say, by doing full like. Or actually, I think I don't even have to pass in a.shape. I just have to pass in a. There we go. If I didn't use full like, I would have to do full of a.shape. I don't know if that's that useful for you, but I guess it's potentially good to know. Okay, next one. Let's say we wanted to initialize a array or a matrix of random numbers. So random decimal numbers to start. To do that, we do np.random.rand and we specify the shape. So let's say 4 by 2. No, what did I do wrong? To do that, we do np.random.rand, and we specify the shape. So let's say 4 by 2. No, what did I do wrong? I'm actually confused. Tuple state. Oh. Okay, yeah, this one's a little bit different. So instead of passing in a tuple, you can pass in directly the integers you want to, integers of the shape. So it's a kind of a weird thing to remember. So if I did the 4 by 2, in this way I would actually pass it in like that. And when you get errors like this, oftentimes you can just do a quick Google search and realize that that's what you need to do. So I can even keep going. So I can do a 4 by 2 by 3 of random numbers between 0 and 1. I could also pass in something like a.shape. I don't know if this would work. Let's try. Yeah, so if you wanted to pass in like a shape, you can do random sample a.shape. And that, now you see, gives us the same shape as our a from up here. So yeah, rand, and then there's random sample, which is another method. We'll keep it as rand of 4 by 2. Okay, what if you didn't want just decimal numbers, but you wanted random like integer values? Well, to do that, we can do random.rand, I'm getting np.random.rand int, and in this one we're going to pass in the start value, or if you don't specify a start value, it's going to just start at 0. And so if you don't specify a shape, then it's just going to do one number. So let's say we wanted a 3 by 3. What did I do wrong? And this is not shape, it's actually size. And yeah, all the documentation has these, like, you know, you're not expected to memorize all of these things. What I think it is helpful to see is that you see that you can do these types of things. So like when you're thinking about a problem, you can like kind of point back like, oh, I remember that that's possible. Maybe do a Google search on how to get it. But yeah, random.randint 0 to 7 with size 3 by 3 is here. I could also specify like a different parameter. So let's say I wanted 4 to 7. And I think, and if I keep running this too, it's kind of cool. You can see it changing. And so it looks like that 7 is exclusive. So if I wanted to include 7, I would stop a little bit later. You could also throw in like negative numbers here. Cool. All right. What else other than random integers? Maybe you wanted to do like the identity matrix. You can do identity of 3. And this one only needs one parameter because the identity matrix by its nature is going to be a square matrix. What else is useful? Maybe it's useful to repeat a array a few times. So to do that, you could do, say we had the array 1, 2, 3. And let's say I wanted to repeat that 3 times. Pass in the array you want to repeat, and then let's print R1. See what happens. and then let's print R1. See what happens. Okay, and then if I specify the axis equals 0, oh no, it didn't do anything. What I can do is make this a two-dimensional array. I think because it was a vector, it didn't do what I wanted to. What I want it to do is 1, 2, 3, or 1, 2, 3, 1, 2, 3, 1, 2, 3. So if I wanted to do that, now I made this a two-dimensional array, and it will repeat the inner part on the 0th axis. Because of it, okay, let's print R1. See what happens. Okay, and then if I specify the axis equals 0, oh no, it didn't do anything. What I can do is make this a two-dimensional array. I think because it was a vector, it didn't do what I wanted. What I want it to do is 1, 2, 3, or 1, 2. Two, 3, 1, 2, 3, 1, 2, 3. So if I wanted to do that, now I made this a two-dimensional array, and it will repeat the inner part on the 0th axis, so I'll be basically making it rows. There you go. So I made this a two-dimensional array, and it will repeat the inner part on the 0th axis, so I'll be basically making it rows. There you go. So if I made this equal to 1, that's going to be what we saw before. Cool. Okay, so next, here's a picture of an array I want you to try to initialize using everything that we kind of just went through. So all these, I want you to try to initialize. using everything that we kind of just went through. So all these different methods. So look at this picture and then try to put it together without just manually typing out all the numbers, because you can imagine like this isn't too big, but if you got into a matrix that was massive, you'd want to know how to build it up using these kind of like fundamental concepts. Okay, so here's the solution to that. So I can do output equals, I'm going to start with making everything ones. So ones, and it's going to be a 5 by 5 of ones. Print output. So this is what I have now. Okay, and now basically what we're going to do is fill in this middle part with zeros. So z, I'm going to just say equals np dot zeros, and that's going to be a 3 by 3. And if I print z, now we have this. Now what I can do is fill in the middle element, so that's 1, 1, with a 9. And now if I print z, we get this. And then finally, we need to replace the middle part of the ones matrix. So output the middle part. So that's going to be the first row to the third row. So I want the first row to the third row, and then I want the same thing with columns because it's the middle. First column to the third column, and actually this is an exclusive value, so it needs to go to 4, and that's going to equal z. And now what happens when I print output is, yay, we got what we're looking for. And actually, one thing that I think is nice is instead of using 4, I could also do -1. So basically, from the first element to the last element, do that. And as you see, it didn't change. This last initialization I want to go through, I guess, is a little bit different. It's over on the concept of copying, but it's something you got to be really careful about. So I'm just going to quickly mention it. I want to do exclamation points. There we go. Okay, so imagine we have 2 arrays, or we have 1 array. Let's call it A. And so, A is just a normal array, as you can see. And let's say we want to make B a direct copy of A. So now I'm going to just do B equals A, and then print out B. And as you can see, it's still 1, 2, 3. And so I'm like, okay, I have this copy, like things are cool, it's fine. I want to change the first element in B. So I'm going to do B0 equals 100. Here's the issue. I print out B, looks good. The issue lies in if I print out A, look what happens. I want to do exclamation points, there we go. Okay, so